Now, with all the knowledge about the distributions, we will explore the meaning of the parameters of the normal distribution. There are many names for them: mean, standard deviation. They are often labeled in Greek, like mu for the mean and sigma for the standard deviation. You can ask the system to generate you some data with the parameters that you prefer. So you ask for certain value of the mean for the data you obtain and a certain value of standard deviation. What is mean and what is standard deviation will be clear a bit later. Then you take the data, you use very basic formulas, and you estimate the mean of the data and the standard deviation of the data. And you can compare what you obtain with what you ask. So this is a certain circularity we have in our reasoning. First, we look for data with given properties, and then we try to identify if the properties correspond to what we ask. And if they don't, this is bad chance. So we generate our data with the mean as 0. Is it 0? Well, let's see. Okay, so we expected to get mean at the level of 0 and sigma, standard deviation, at the level of 1. Our results are close to what we expected. So you see, the mean is very close to 0, and the standard deviation, which is marked with those whiskers, is also pretty close to 1, but not exactly 1. And if you rerun the same procedure, you will see that you get different values, and they are still not absolutely accurate. There is always some variation. Here you have a very important difference between what we asked for and what we obtain. Why does it happen? It's not because of the error of the program. It is because our data is random, and there is random variation of the obtained mean and the obtained standard deviation purely by chance. If we decrease the number of samples, then this variation becomes more important. You see, it is 0.2 instead of 0. And next time it can be minus 0.15. On the contrary, if you increase the number of samples, you get much less variation of the statistical parameters in comparison to what we requested for. This is a general rule. The more is the sample, the more is the precision, and the less is what is called statistical error or statistical noise. Now, what can be qualified as normal distribution follows certain rules of how much data is observed within the range of 1, 2, or 3 sigma, or standard deviation. So if you take the interval between mean and minus sigma minus standard deviation and mean plus standard deviation, you must have something like 70% of your data within this range. And obviously much more if you take 2 sigma interval or 3 sigma interval. Still, even if you take 3 sigma interval, you don't have all the data. And with this kind of distribution, it is impossible to get all the data, whatever is the range. There will be always some very small chance that you get your observed data very, very far from the mean. But obviously this chance is minor. Now we will try to replicate this rule in our data which are generated. And you see that the rule is more or less replicable. About 60, 70 in the interval of plus minus sigma, much more, 90 something percent in extended range of 2 sigma, and in this case 100% of observations within the range of 3 sigma. If you run it again, you will see a different result, but still the numbers are comparable to what is expected. And if you want to get better precision, you increase the number of samples and you get numbers which are really close to what is expected theoretically. Now, let's generate the data and plot our data with the sigma marked on the histogram. Our data is here, and it is a very large sample. Now, I think for our purposes, it is better to have a smaller sample because we will try to see if there is an impact of the size of the sample on the order of the magnitude of the mean and the standard deviation. As you can see, it is not the case. The mean and standard deviation is always more or less the same. Its variation is more if the sample is less. But mean is 1 as expected, and the sigma is also 1 as expected. Can we conclude, if we look at the data, if our data is different from 0, which is marked in dashed line? Actually, this is the question which we ask every time we run an experiment and we test a hypothesis. If this is better, worse, bigger, smaller than certain reference point. If there is a significant increase after intervention or something like this. What we observe now give us an idea of a trend, but we don't know if what we observe is there just by chance or because there is really something in our data which is sufficient to conclude that the mean of 1 is different from 0. A classic approach is to estimate 95% confidence interval, which is the interval where we 95% sure that the mean is located. So we believe, based on the number of samples and the standard deviation and the mean, that the mean is within this range. And this is good because our hypothesis is confirmed. Our result is significantly higher than 0. If we increase the sample size, which we can do in cell 3, we will see that the confidence interval will be reduced dramatically. The sigma is the same, but the confidence interval is really tiny, which means that our data is very certain of being significantly different from 0. Now let's generate some data where the result is different from 0, but not significantly. Let's make it with just 30 samples. The sigma is the same, but the mean is only 0.2. It is still a normal distribution. The sigma is still as expected. The mean is somewhat different from what is requested, but this is something we can imagine as well. It happens by chance. But what about our statistical conclusion? Whether our data is statistically significant, or in other words, whether we are 95% sure that the mean we observe is superior to 0. If you look at this confidence interval, it is not significant anymore. Just a small comment, the confidence interval, the student-based confidence interval, is computed in a simplified way here. Being computed correctly, the formula will be somewhat more complicated. But we don't require this kind of precision at the moment. So this is a rough approximation. If in this case we increase the number of sample, our confidence interval will be reduced. Our certainty about the mean will be higher. Let's increase it slightly, just 2 times, and see what happens. It is the same mean as the same sigma, but a greater sample. We plot the histogram, sigma the same, the mean. Now it is smaller, as you see. There is always some variation. And this is actually what makes us have doubt in where the mean actually is. You see, it is still not significant. Very close, but not significant. So let's do something to be sure that the result is significant. We increase the sample size dramatically, 10 times. We build histogram. The histogram is more beautiful. Now it looks really like the bell, like the normal distribution. And the confidence interval is small enough so that we can conclude that the mean is significantly different from 0. The hypothesis is confirmed. Now we will use a different approach to estimate the confidence interval, which is called bootstrap. What we do here, we take randomly the values of our data, which is XX, which is a large array of the data of 600 values. But we sample randomly from this data, and we estimate mean, and we save it. And we repeat this simple procedure many, many times. In this case, 10,000 times. So at the end, we will get 10,000 values of the mean obtained from the same original data array. But those mean values will be variated. They will not be the same. They will form another distribution. And based on this distribution, we can easily estimate the confidence interval, the bootstrap-based confidence interval, based on the percentile. So we cut off the smallest 2.5% and the largest 2.5% of the distribution. And we get exactly what we need, the confidence interval, or 95% confidence interval. Let's see what happens when we do it. We get another confidence interval, which is very much the same as the confidence interval estimated with a much simpler formula of student. Why is it so? Because the student formula is based on what is obtained in this kind of manipulation. Multiple sampling from the same global data array. And the last cell is to illustrate how the bootstrap distribution looks. So this is the distribution of the means obtained from randomly sampled real data. And those green lines, they cut off 2.5% from the lowest side and 2.5% of the data from the highest side. The sum of all the values is 1. This is the probability of the observation of different values. And then this interval is shown at the top of our original data, which is clearly indicating that our data is different from 0. Both approaches are valid as soon as you have your data normally distributed. This is an important assumption. In case of nonparametric data, which have different distribution, it's preferable to use nonparametric tests. One of them is the bootstrap.